Welcome to the Explainer. So today we're embarking on this really fascinating journey into what I like to call the hidden energy vault of physical systems. Have you ever actually stopped to wonder how the universe just parks its power when it's not actively using it? I mean, how does a machine, a circuit, or even the natural world around us hold on to energy for later? Well, that's exactly what we're decoding today as we explore the dynamic state, capacitance, inertia, and energy storage.
Think about this for just a second. What do a tightly coiled spring, the battery sitting right there in your smartphone, and a massive, high-speed moving train have in common? On the surface, I know, they look completely, totally unrelated, right? One's mechanical, one's electrical, and one is literally a massive vehicle in transit. But underneath it all, speaking the language of physics, they're actually utilizing the exact same universal concept. They are basically acting as energy storage lockers. And as we'll see, understanding how these lockers work is really the key to unlocking the dynamic state of pretty much any physical system.
Okay, let's dive into section 1, meet the storage duo. So I want to introduce you to our primary characters here, capacitance, which is our C element, and inertia, our I element. I really want you to think of these two as the ultimate dynamic storage duo. They're basically the universal lockers where nature parks its energy. But, and this is a big but, they do not store the same kind of energy. Capacitance is all about storing potential energy. That's energy that's just waiting to be released, and we link that with displacement. Inertia, on the other hand, well, that's the locker dedicated specifically to kinetic energy, the energy of actual physical motion, which is tied directly to momentum. So they're really two sides of the exact same energy storage coin. Moving right along, we arrive at section 2, capacitance, and the storage of potential energy. Now, what's genuinely interesting about this is the specific variable we use to define this state. It's Q, or displacement. When we talk about capacitance, we aren't just talking about electrical circuits, even though, yeah, that's definitely where the word is most famously used. In a broader physical sense, capacitance fundamentally works by storing energy as some form of physical or electrical displacement. Basically, you're displacing something from its resting state, and by doing so, you're banking potential energy. It's kind of like pulling back a slingshot. That variable, Q, is the exact measure of how much potential energy is just sitting there in that C locker, completely ready to snap back into action. All right, let's pivot to the second half of our dynamic duo, section 3, inertia and the storage of kinetic energy. So if capacitance is all about holding energy in this tense, displaced state, well, inertia is kind of the complete opposite. It acts as the dedicated locker for kinetic energy, holding onto power purely through motion. And the variable that tracks this? That's P, representing momentum. Whenever you have mass on the move, you have energy being stored right there in that movement. Inertia essentially preserves that kinetic energy. I mean, it's the exact reason a really heavy object is incredibly hard to stop once it gets going. The momentum, P, is quite literally the physical accounting of that stored kinetic energy. Now that we know our two primary variables, let's move to section 4, the Energy Vault Challenge. Okay, let's see how this builds our intuitive understanding. Welcome to the Energy Vault. I'm going to present you with those exact same 3 objects from the beginning of our explainer: a spring, a battery, and a moving train. Your challenge right now is to test your intuition. Ask yourself, which universal storage locker, capacitance, or inertia is each object utilizing to hold its energy? Try to figure out if they're storing potential energy through displacement or kinetic energy through momentum. All right, let's see how you did. First up, the spring. When you compress a spring, you're physically displacing it from its resting state. Therefore, it's a mechanical C element, mechanical capacitance. Next, we have the battery. Now, this one holds electrical charge that's separated in a state of potential, so that makes it an electrical C element. And finally, the moving train. A massive object just barreling down the tracks is the absolute ultimate example of momentum. That makes it a mechanical I element, mechanical inertia. By categorizing things this way, it's actually amazing because we can see the exact same physical laws at play across completely different systems.
Let's elevate this from these practical, everyday examples to section 5, the tetrahedron of state. This brilliantly illustrates the mathematical relationship between power variables and a system's true state. Let's look at the logical flow here. We start in step 1 with action, so that's either effort or flow happening in real time. But the big question is, how do we get from raw power acting in the moment to the energy parked securely in our storage lockers? Well, the answer is step 2, apply integration over time. When we apply that integral, mathematically speaking, we're basically accumulating that action over a period of time. Integration acts as this vital bridge connecting power to storage. And naturally, that leads us right to step 3, where we finally arrive at our defining storage variables, momentum P and displacement Q.
So here's the really crucial point to take away from all this. The P and Q variables, they aren't just random letters in a physics textbook. They ultimately and completely define the entire energy state of literally any system you encounter. Once you know a system's momentum and its displacement, you've essentially just read its energetic DNA. This concept gives us a really comprehensive understanding of the big picture, because it links physical movement directly to stored energy. It's basically mapping out exactly how the universe saves its work.
Which brings us to our final thought. I want you to literally take a look around you right now. The chair you're sitting on, the device you're watching this explainer on, even the air circulating in the room. What are their energy state variables? Where is that hidden displacement Q storing up potential energy? And where is the hidden momentum P storing kinetic energy? You see, once you start looking at the world through the lens of capacitance and inertia, you suddenly realize that absolutely nothing is truly static. Everything is just an energy vault, just waiting to be opened. Thanks so much for exploring the dynamic state with me today. And hey, never stop questioning the forces shaping the world around you.